Hello everyone. Wish you all a very good evening. How's it going? Cool. Awesome. So guys, as usual, there are a couple of announcements. Let me go ahead and pin the message so that it's easy for you to find. Uh, so on April 29th at 11 a.m. we have a session with one of your peers. It's a roadmap to data analyst offers. So you can register for this event over there if you're interested. So cool. Otherwise, how's it going, guys? End of the week, so we can expect lesser attendance today as per the pattern we've been observing. Is it just me or is the weather getting hotter? Okay, wow. All right, let's just wait for more people to join in. With 3 minutes into the lecture, we will start at 9:05 as usual. So cool. Let's wait for more people to join. In the meantime, I will just prepare a couple of things. All right, guys. Almost time to begin. I hope all of you are doing well. There are very few people in class today. So let me just greet everyone who is here. Ajay, Anindya, Indradeep, Renu, Srinath and Sumit. Wish you all a very good evening. I'm so stable, so you thought internet is not working. I don't know, man. Like nobody was responding, so I was kind of just waiting for people to join in and respond. Can you guys confirm you can hear me and see my screen? Is my screen readable? Uh, Generally, you have to give me the OTP, right? Can you guys quickly tell me the OTP so that I can confirm that you can read my screen? Let's wait for that. Awesome. 7763. So the OTP is given. Thank you so much for that. Cool, guys. So let's begin another lecture in this topic, natural language processing. Cool. What we're going to study today is language modeling. And I'm pretty sure you guys have come across different applications of this before. But what we're going to do is we're going to take a technical look at this topic, right? Okay. So let's begin. Before we begin, Ajay has a question. Good time to ask a question, right? Have a question. How can we do quantization to save space by storing the embeddings? So Ajay, in the neural networks module, right? I'm pretty sure someone may have introduced you to this library called TensorFlow Lite. So TensorFlow Lite is basically what you use for all these kinds of tasks. So there are three ways of saving models. Saving this thing, right? You can either prune your network, you can quantize your model, or you can do a third thing. The third thing was knowledge distillation. So TensorFlow Lite actually allows you to do all three. Let me just show you this quick. Right? So TF Lite actually allows you to do all three. It's possible for you to use this. Is that good enough? Ideally, it should have been introduced in the neural networks chapter, like module, right? If you have any further doubts about this, maybe you could take a look at the guide and this thing. So TensorFlow Lite is like really well documented, and it's kind of easy to follow through. So you could sort of take a look at this. Okay. Anyway, coming back to our main topic at hand, we are now studying language modeling. Let's begin with the usual recap, right? It's very nice to know why is it that we're studying and how is it related to the overall field, because ultimately what we want to learn is transformers, because ChatGPT is essentially a transformer, so we want to know how that stuff works, right? But it's important to go step by step and see how this topic fits in the overall picture. That way we can be confident that if some new variation comes, we can quickly learn it, adapt to it, and apply it to our jobs, right? That is our basic motive here. So let's begin with a recap. Again, I'm going to start with a recap of these terminologies. I know it's a bit repetitive, but please bear with me. A corpus is a collection of documents. Documents are collections of one or more sentences. Sentences are collections of words, right? And broadly speaking, the last few classes, we have been focusing on this one basic problem, which is how do I convert a text data set into vector form? Why should I even need vector forms? Can somebody quickly remind me? Why do we need to convert text data to vectors? Any idea? Anyone? Please remind me. I have 5-second memory. I've forgotten everything I've ever learned. Nobody wants to help me? Come on, man. Come on, guys. Why do we need to convert text data to vectors? I'm going to pause till somebody answers me. I cannot bear teaching an uninteractive class. So somebody has to answer before we move on. Otherwise, there's no point, right? I'm just shouting at myself. Okay, Ajay says to build a matrix. Okay, to build a matrix is a good start. But why do we build a matrix? What is the ultimate aim? What's the ultimate aim of converting text data sets to vectors? This is a small class, guys. You can be more interactive. Come on. Why do we need to build matrices? What's the whole point? What are we doing here? Compare embeddings, okay. Compare embeddings, finding relationship between words. All of these are valid. These are valid applications of this thing, right? Perfect. So overall, generally, if someone asks you this in an interview, the answer should be because all of machine learning depends on vector representations of data, right? Broadly speaking, from a very high level, that is why we do this. We want to apply machine learning techniques to solve these problems. It's always a good idea to convert whatever problem we have to a set or a fixed method which has already been explored and then proceed with it, right? And all the answers that you guys have given me are a part of that. So, for example, if we want to apply SVD to get embeddings, building a matrix is a good idea. And then this is compare embeddings, right? So once we have the vector form, to find things which are similar to this, we can apply cosine similarity between vectors. That is why vectors are very useful. Finding relationships between words, again, is a very good way to do this, right? The relationships can come through the vector forms of these textual data, right? And broadly speaking, we've seen two methods of converting our text data into vectors. Okay, Satish has another answer. With vectors, we can create sparse matrices which help separate words which are easy to visualize and modules to able to converge easily. Perfect. Okay, that's a nice technical answer. It's quite accurate. Usually, it's a good idea to use sparse matrices and decompose them because that gives you a really good idea of how your embedding space looks like. So that's great. Moving on. There are two ways we can convert text data sets to vectors. We can either work at the document level or we can work at the word level, right? So the methods for vectorization are bag of words, TF-IDF, continuous bag of words, and skipgram. These are the methods that we have studied so far. Can you guys quickly tell me, out of these four that I have written here, right, which one will help me convert a whole document to a vector? Which one will help me with this task of converting document to vector? You can just give me the numbers. So this is number 1, this is number 2, this is number 3, number 4. Can you guys just tell me quickly which of these four methods will give me document to vector? Okay, TF-IDF, perfect. 1 and 2. So I got 1 and 2 for document to vector. So 1, 2 is for document to vector. And for word to vector, what is it? What is it for word to vector? The remaining ones? Isn't it obvious process of elimination? Can I write 3 and 4 over here? Yes or no? Hit a yes, man. People, come on. Let's do this properly. Right? We're here to learn. It doesn't help if you're learning passively. Let's get active. Okay? Cool. So 1 and 2 is document to vectors. Word is 3 and 4. Right? Okay. Okay. Prasad has asked me for a small recap of all of these. Let's quickly do that. Sure. Bag of words essentially is simply taking your sentences. Okay. You take your entire corpus. You find the vocabulary. What do I mean by vocabulary? The set of all unique words inside my corpus. Okay. All unique words inside my corpus is the vocabulary. All I'm going to do in bag of words is I'm going to put a 1 or a 0 if the word is present in a given document or not. Right? Another way to do the same thing is by using the term frequency. So instead of just putting a 1 or 0, I'm going to put a count of the number of times this word has appeared in that document. So that is how bag of words works. Okay. TF-IDF works is TF-IDF essentially builds on top of bag of words. So the problem with bag of words is this representation is just for a document. It doesn't tell you anything about how important or unimportant a word is with respect to the rest of the documents in the corpus. So the job of TF-IDF is to give you some idea how important is this word with respect to the whole corpus. So that is why we built the TF-IDF using the techniques that we discussed 2 classes back. Then last class specifically, we looked at word to vec, right? Words to vectors. So in word to vec, we saw the continuous bag of words form. If you guys remember, this is similar to a very nice problem that used to be asked to us in our 10th standard. Can you guys quickly tell me, continuous bag of words is similar to what problem in our 10th standard? Fill in the blanks, exactly. So continuous bag of words is like fill in the blanks. If I give you 4 words, you have to tell me what words fits at the center. Okay. Skipgram is also very similar to something we have learned, something we did in our language classes. What was skipgram similar to? Quickly. Skipgram is similar to what? It's similar to essay writing, right? Perfect. So if I give you one word, you have to tell me what words fit around that. Okay. So broadly speaking, these are the different methods of vectorization that we have learned. Correct? So this is what we have. Cool. So this completes our recap. Now let us go ahead and see the rest of the agenda for today. Okay. Today what we're going to do is we're going to do language modeling. So what does language modeling basically mean? It is how to teach a computer to form sentences. Now we are starting to get very ambitious. Before, when we were doing skipgram in the last class, all we asked our model to do was tell us the most probable words around this word, right? But today we're going to try and get it to form entire sentences, not just 4 words in some window. No, we're now going to get our computer to predict what the entire sentence is going to be. So that is language modeling, and that is the main topic of today. Okay. So we are going to now try and solve this problem using whatever we have learned. So I'm going to spend some time taking ideas from you guys, building on top of that, discussing the probable pitfalls and all that. And then we will go and study some techniques which are well used in the literature. So the techniques which are well used in the literature are unigram, bigram, trigram, n-gram. All these methods are essentially used by people to implement language modeling. So we're going to take a look at that. These concepts that we're going to learn today essentially form a very nice basis for learning recurrent neural networks. Okay. So whatever we're going to do today will form the basis of recurrent neural networks, which we're going to study in a few classes. So it is important to understand the math behind how these techniques work so that we can convert this math idea to the neural network architecture, which will finally do something very, very useful for us, right? So that's the motivation for learning these things. The core concept that we have to recollect is conditional probability, okay? And before we go ahead with the technical details of this, let us quickly see first what's the business case. Then we will come back, we will talk about conditional probability, and then we will dive deep into these techniques, okay? Cool. So let's do that. Let's look at the business case that we have for today. So the business case for today is email autofilling, okay? Or text message autofilling. So imagine that you're working as a machine learning engineer at Google, specifically Gmail, Okay. You have to design a product which basically allows you to predict what is the next word. So guys, have you encountered this feature, by the way, in Google? Like when you're typing an email, right? If you it will actually suggest some word to you. You can press tab and it will autofill that. So the question that we have to the problem that we have to solve today is how can we build this product? Given a part of the sentence, what should the next word be? That is what we're going to go ahead with. Okay, cool. Now, apart from this autofill that is there, what are the other applications? So one application could be suggestion of different prompts. So something like if you try to search ngram in Google, you will see ngram Python, ngram module, all these kinds of things, right? So this is another possible application of the same thing. People from my generation and above will probably remember these old Nokia phones that we used to have, right? The ones with those dial pads. Do you guys remember what those used to look like? Those Nokia phones with those dial pads. So do you guys remember that on those Nokia phones, right, we could actually just type the numbers and it would predict what word would come, right? Do you guys remember that? It was called T9 prediction, by the way, in the years. So this was very, very popular in like between 2002 to 2010, somewhere in that area. Yeah. So if you are born after that, probably you don't know about it. But in that age, we used to have this T9 dictionary prediction. Yeah, exactly. T9 dictionary they used. It used to basically predict. So if I wanted to spell the word cat, right? So just one moment. Let me quickly pull what a dial pad looks like. So phone dial pad. Cool. So this is what we have. Let me quickly get this picture over here and let's discuss this, right? Yeah. So for example, if we have something like this, right, and I wanted to spell the word cataract, for example, right? If I wanted to spell the word cataract, if I press 2 and 2, right? If I simply press 2 and 2, it would actually start predicting the word that I would this thing. Why 2 and 2? Because the word C appears here and the word A appears here. So I want this mobile to basically take up C and A, and that essentially helps me predict what is it that I'm trying to type, right? So in fact, the method that was used to design this, right, is exactly what we're going to be studying in detail today. So just a little bit of a side problem. So T9 prediction also use the methods that we're going to be discussing today, and essentially this is going to be the business case. Okay, cool. So now let's come to naive approaches to this. Using whatever we have learned so far, guys, like in the past few classes, whatever we have learned in the, let's say, machine learning module, supervised or unsupervised, let us see if we can come up with some features or some methods to solve this problem. Can you guys suggest any methods to solve this problem? Any naive approaches? Any methods? Anything? Absolutely any ideas are welcome. But think of this as an interview session where I'm asking you to solve this problem and tell me how you would approach it, right? So any answer is fine. Please let me know. Yeah, conditional probability. Okay, perfect. So Indradeep, you have taken my answer from here, right? Try a little bit of creativity, right? So conditional probability. What does conditional probability remind you of? Any machine learning technique which uses conditional probability? Naive Bayes. Perfect. Yes. Conditional probability, so naive Bayes. Cool. So naive Bayes is one way of doing that. Narendra is saying cosine distance. Perfect, Narendra. So Narendra is saying basically, if I now first convert my entire email into one of these two vector forms. Okay, Narendra, which one do you think is better? Do you think a word vector form is better or a document vector form is better for this? Which one do you think is better for this task? Word vector form is obviously better, right? Ajay says, yeah, word vector form is obviously better. Why? Because documents don't really help us. We want to now start predicting words. So if we now first convert our entire corpus into word vector forms, learn word vector representations, and then use something like cosine similarity to predict the next word, that is one strategy. Narendra, from our experiment last class, right? We did some experiments with word to vec. Do you remember when we were giving query words to COVID, right? If I said origin of COVID, it actually went to pathogenesis, right? So it learned words at a conceptual level. Okay. So can you tell me, Narendra, if I first convert my entire text to word forms, okay, the cosine similarity, will it give me similar words or the next word? Which one is more likely? Similar words or next word? Similar words, right? So does this solve our problem? Does this solve our problem? Does it solve our problem? Yes or no? It doesn't, right? It doesn't really solve our word. No, no. So cool. I'm happy that you thought of it that way. I'll still put it down. I'll still put it down. I love the answer. It used whatever we have learned so far, but it will not work here. Okay, cool. So let's put this down. Word to vec followed by cosine similarity. Oops. Okay. Word to vec followed by cosine similarity. Problem is it gives similar words. Maybe not so useful. Right? Okay. Seba also used maybe, sure. But Ajay, if you remember last class, both Seba and this skipgram solve the same problem, right? It is a word to vec strategy. Again, word to vec always gives us similar words. It is not going to predict the next word, right? So that is why the problem we're trying to solve today is very different from the problems we've already seen, right? That is why we have a new topic for it. So yeah, okay. Deepak says, can something like a priori be used since we want the words to occur together? Perfect, right? Deepak, you're absolutely correct. A priori is something we're going to consider when we are looking at the conditional probability part of this, right? We're going to look at that. So when we're developing this model, we're going to look at it. Guys, come on. Anything else? Any other strategies? Narendra, there is a very nice thing you can do to make this work. Can you think of some way to make this work? Your suggestion is actually good. If we do word to vec, is there something we can do, some modification we can do to word to vec, right? Some modification. You're on the right track. So a lot of modern techniques to do language modeling start with word to vec. So can you think of how to make it work? In the meantime, let me take Satish's question. Can we use SVD if word vectors are comparatively small? We can. If our vocabulary is small, we can. But think about it, Satish. Gmail is a free service. There are millions and billions of emails which are lying with Google, right? If it has to learn something, it has a huge data set. So SVD is not that practical. SVD works when you have small data sets, right? But here we have a huge data set. So that's probably not a great way. Okay, cool. So guys, let me give you one naive method which I thought of when I was preparing for this lecture, right? Let us dive a little deep into the fill in the blanks task, right? Basically, what I'm asking you to do when I'm saying sentence formation, isn't it like a fill in the blanks where the blank is at the end of the sentence? Where the blank is at the end of the sentence? Can you guys think of it that way and come up with a technique? Can we make some change to our one of these two word to vec strategies, right? Can we make some change to that and get it to work? Tell me, please. Indradeep says, what if we train word to vec differently and teach it to predict next word? Perfect, right? So RNN. That becomes RNN. Yes, that becomes RNN. So Narendra, no. It is not bigram. Word to vec uses bigram models, but at the end of the day, we can modify this bigram method. We can modify this continuous bag of words method, right? If you remember, continuous bag of words is like fill in the blanks. If we take this continuous bag of words architecture, modify it so that the blank comes at the end of the sentence, then don't you think it will work? So bigram here, Narendra, will be based on whether I'm using two words to predict the last word, right? It will become bigram if I'm giving only two inputs and I'm asking you to fill in the blank. If I'm giving you three inputs and asking you to fill in the blank, it will become trigrams. All these things will come, right? So we're going to discuss these one at a time. But this actually is the most popular way of doing things, okay? So the naive approach that we can have is take CBOW, okay? I hope you understand what CBOW is, right? CBOW is continuous bag of words, okay? If you take CBOW now and you modify it to produce the last word, we could have a neural network solution. Okay, cool. So perfect. I'm really happy. This class together, we have been able to figure out so many ways of solving this problem, out of which today's focus, guys, is going to be on this approach. Okay. Today, we're going to try our best to solve this problem using just conditional probability. We're going to see some issues with this. And there is a very, very good reason why we want to use conditional probability over a neural network solution. Okay. And the answer is kind of straightforward. Can anybody guess why or in what situation is this conditional probability approach better than CBOW? I'm basically asking you, what makes naive Bayes better than neural networks? That is the question I'm asking you. So can you guys quickly tell me what makes faster than NN, right? Faster, time complexity, it will require lesser memory, right? Memory and time are both very, we can optimize both memory and time well if we start with naive Bayes, right? And we will need lesser data. Perfect. Okay, cool. So you guys are on the right track. Awesome. So this is a very good reason why we should use conditional probability on top of instead of CBOW. Okay. So today our focus is going to be on conditional probability approaches. Okay, cool. So before we start, I just want to recollect some conditional probability concepts so that it's easier to talk, right? So some conditional probability concepts I just quickly want to recall. Once we recall that, we will proceed with the actual technique, right? Okay. So I sincerely hope you guys still remember what probability and conditional probability is, right? Okay. So in probability theory, we generally have events, right? So I have A and B, which are both events, okay? The probability of the event A is given by this P of A. The probability of event B is given by P of B, okay? Now, if I want to ask you what is the probability of both A and B happening at the same time, how will you write it? How will you write it? A given B? No, Indradeep, right? A intersection B, right? Guys, A and B. I want A also to happen. I want B also to happen. If both are happening together, then I want A and B. So this becomes A intersection B. Okay, cool, right? Now, guys, generally when we write, so this is A intersection B. Now, using this idea, right, we can actually come to the concept of conditional probability. So now, what is conditional probability? Conditional probability, I'm basically asking you, I'm giving you some information, and it's your job to tell me what is the adjusted probability if this information is true, right? For example, let's take an example. Let us look at this P of A given B, okay? This is what Indradeep just said. This is conditional probability, but let us understand how to interpret this, right? To interpret this, what we basically have to do is we have to think what is the probability of A happening given that B has already happened, right? Given that B has already happened, what is the probability of A happening? And if you guys remember your conditional probability and PropStats lectures, you might remember this formula, right? P of A given B is nothing but P of A what? P of A what? And what is in the denominator? P of, can somebody remind me quickly? Satish's answer is, A intersection B, right? Perfect. So A intersection B will come in the numerator. In the denominator, we will have P of B. Perfect, right? Okay. So now, whenever we're talking about conditional probability, we have to remember, we basically want to put P of A intersection B in the numerator, P of B in the denominator. This is what conditional probability looks like. One final point of recollection, right? What if I know this already, and what if I wanted to find P of B given A now? How will I do this? What will I apply here? If you just give me the name of the theorem, that's enough for me. What will I do now to flip this? Bayes theorem. Perfect. So using Bayes theorem, if I already know P of A given B, I can figure out P of B given A as follows, right? P of B given A is now going to be P of A given B into P of B, the whole divided by P of A. Okay. So now, if these ideas are clear to everyone, we can proceed with studying the details of today's techniques. Is everyone okay with this? Any doubts over here? Any extra recap needed? Please ask me right now, because it will be very difficult to go through this lecture if you don't remember these concepts. right? Okay, perfect. So a lot of people remember these concepts. Let's do it now. Cool. So now let's apply these concepts to understand how we can do language modeling. Okay, cool. Okay, so now Vishwarup's question to me is, are we studying base theorem? No, Vishwarup. I'm basically revising base theorem because I'm going to apply it now. I wanted to just ask that so that we are comfortable with applying it to this problem, right? That's all. Huh. Ah, no, no, no worries, no worries. That's okay. That's okay. Okay. So guys, let's continue now. The first thing I want to start with is how to apply conditional probability concept to predict the next word. Okay. Now I want to ask you guys, I'm already telling you, I'm saying that the answer is conditional probability. How can I now use this conditional probability to predict the next word? Okay. Let's take an example to understand this. Okay, let's take an example to understand this. The cat is dash, right? So essentially, I'm now giving you a context here. The cat is dash. Okay. I'm basically asking you fill in this blank. Okay. What is one possible strategy that I can use? Let us say, okay, let us say I already knew the conditional probabilities that are required to solve this problem. Can anybody think of a way to do this to make the notations easier? Right? Let me do this. I'll call this word 1, I'll call this word 2, I'll call this word 3, and what I want to predict here is word 4. Right? What I want to predict here is word 4. Okay. Let us say now I have a vocabulary with me. This vocabulary contains many words. Okay. Let us say it contains word 1, word 2, word 3, all the way up till word n. Okay. Where n is a very large number, something like 3000. Okay. 3 to 8000, something like that. Very large number. How will I now say out of all these words, which word should come here? Right? Out of all these words, which word should come here? How do I do that? Prasad has given me an answer in the private chat. Let's see. Okay, Indradeep has also given me the answer. Perfect. Okay. Let me go with Prasad's answer first, then I'll come to Indradeep. Find a word with the highest probability given the previous 3 words are the cat is. Perfect. Okay, so both of you together have given me the answer. I am now going to say word 4 is nothing but the word which maximizes the following probability. Okay. Word 4 is nothing but the word which maximizes the following probability. So essentially, I want to find argmax, right? I'm saying word 4 is nothing but argmax of, with respect to I, P of Wi given W1 equals to the, W2 equals to cat, W3 equals to is, right? So any word which maximizes this conditional probability is nothing but the word which I will predict as the next one. Okay. This is now going to be my strategy for predicting the next word. What's nice here is that I have this conditional probability which I have to work with. Okay. Is everybody in class comfortable with how to compute these conditional probabilities? If I give you a huge corpus of data, right? If I give you a huge corpus of data, this conditional probability computation is going to use this formula, right? We simply have to see all the words in my corpus where the cat is has appeared together, right? And given this order, what is the next most probable word? So let us say that we have 3 or 4 sentences in our corpus. The first one is the cat is running towards the mouse. Then we have the cat is pink, or the cat is sleeping on the table, right? Let us say we have these 3. And let us say, since we have a very lazy cat, the cat sleeps a lot, right? Let us say the occurrences of the word sleep after the cat is is a lot of is way too many times. Okay, let us assume this for now. So here in this example, the cat is sleeping is the word which will be predicted because the word sleeping is appearing the most number of times with these three words in the prefix. Okay, that is how we are going to do these predictions. So let us take some examples here. Okay, let us take some examples here and let us dive deep into what are the possible issues that we could face with these kinds of things. So now the whole game is building a predictor using conditional probabilities. Do you guys remember that this is very similar to naive Bayes? Is this or is this not very similar to naive Bayes? Yes, it is similar to naive Bayes. Cool. Narendra's question to me is the answer is dependent on the training sample. Yes, Narendra, it is dependent on the training sample. All these methods that we are now learning, right, the classical methods are all going to be dependent on the training sample. The only method which is not dependent on the training sample is BERT. Okay, so language transformers. Attention is all you need. After attention is all you need paper, only we were able to leverage this. What do you say? Transfer learning for NLP models. Before transformers came, we were not able to find any way to carry over one dataset's interpretation to the other. So all the models we are going to be discussing till BERT are going to be dependent on the training sample. Okay, that's one nice way to nice fact to remember. Okay, cool. Moving on, let us now understand this idea a little bit better. Okay, do you guys remember any obvious problems with working with probabilities? Obvious problems when it comes to probabilities? Yeah, nice. Okay, problems with probabilities. Okay, the first one is, of course, if we have P of W1, Wk given W of k minus 1, W of k minus 2, W of k minus 3, so on till W of 1, right? This is now going to be nothing but, oh, okay, Anil says it's multiplied by 0. Okay, Anil, so there are two issues here. Okay, let us discuss both these issues. First, since this conditional probability is going to be nothing but probability of this intersection, right? The probability of all these things happening together, right? It's so this we can write as the following thing: probability of Wk intersection Wk minus 1 intersection Wk minus 2 intersection so on, right? Divided by probability of Wk minus 1 intersection Wk minus 2 intersection all this, right? The basic issue here is that both the numerator and the denominator are going to have low values. Yeah. So this is one obvious problem when it comes to dealing with probabilities. Okay. How do we fix this problem? How have we fixed this problem in the past? In naive Bayes, we can take the log, right? So the solution for this is to take log probabilities and work with log probabilities. Okay. Now let us come to the second problem which Anil has so nicely mentioned. Okay. The second problem is this. Let us say we have a very, very large data set, but suddenly it's possible that we encounter a new word, right? It's highly possible that in an email we encounter a new word. For example, people are coming up with new words all the time. Before Game of Thrones, we probably never heard of the word Baelish, right? Or Targaryen, for example, right? So people are coming up with words all the time, and most commonly, the words which we come up with are names, right? If you think about it. So how do we deal with words we have not seen before, right? So the second issue is exactly what Anil mentioned. How do we deal with words which you have not seen before, where the probability of that word itself is 0, right? Probability of word equal to 0. This happens when we have not seen W before, right? This is what happens. So in these cases, we have to think of solutions. Okay, perfect. So I'm already getting solutions from people. Indradeep says, okay, from our machine learning class, we have learned something called Laplace smoothing or additive smoothing, right? So Laplace smoothing is one possible solution for this. And there are certain other solutions, right? Yeah, cold start problem in recommender systems. Yes, Prasad, awesome, awesome. I like that you guys are relating these new concepts to old things. Perfect. This is how it should be. Okay, so these are the typical problems that we have with probability, right? So I just wanted to discuss these here itself because we have to keep these in mind. The difficulty of understanding today's topics is going to be with these issues. Particularly, how do we deal with very small numbers and how do we deal with unseen numbers, right? So with these two problems in mind, we can actually go now and start implementing the technique which we have decided here. Okay, we are now going to start implementing a technique which allows us to calculate the conditional probabilities as follows. Okay, so we have to calculate the conditional probabilities like this, and we have to keep them somewhere, and then using those conditional probabilities we have to make some predictions. That is the broad outline of how we apply naive Bayes to solve this problem of predicting. Okay, cool. So let's move on. Let's also focus on one problem which I don't expect you guys to know. Okay, there is actually one more tiny problem which I don't expect you guys to know. Does anyone want, I'll give you a hint. If you're able to solve it, I'll be very happy. But if not, then I'll give you the answer. Okay. Do you guys notice this conditional probability here has this numerator term which has these intersections, right? It has this intersections. So whenever we have this intersection, right, guys, we have to think of this as a joint probability. So there is this concept which is known as joint probability. I wonder if you guys have heard about it, right? Joint probability. Anil, that is the solution to the joint probability problem. Okay, Anil, excellent. I'm really happy. You thought 2 steps ahead. I'm happy, but hold on. Let's discover this, right? First, let's talk about this joint probability. Okay. Whenever we have terms like this, P of W1 intersection W2 intersection W3, so on till intersection Wn, right? If we have terms like this in our in our mathematical equation, what this means is basically what is the probability of seeing word 1, word 2, word 3, all the way up till word n in exactly this order. Right? In exactly this order, what is the probability of seeing the words? Right? That is the naive assumption in naive Bayes, right? Yes, Indradeep, exactly. This is exactly the naive assumption in naive Bayes. What is the probability of seeing this exactly? So the naive assumption basically allows us to break it down into independent probabilities. So I'm happy that you were able to think of it that way. I thought of it slightly differently. So I thought you might not be able to answer, but cool, you guys are sharp. Great. Let's discuss this problem a little bit now though. Okay, it's important to discuss this problem in this context. Guys, usually when we form sentences, right, almost all sentences are unique. It's very, very rare for us to form sentences which are exactly of the same pattern, right? Unless you're in 5th standard and you're just learning how to write essays, you will have a specific template, right? So just imagine yourselves in 5th standard. And one of the most common topics used to be my pet, right? My pet. So the teachers used to give us this template. My pet's name is dash. My pet is a boy or a girl, right? Boy or a girl. Then my pet's color is dash. Right? So over here, if you notice, this word my pet is occurring together many, many times. Right? But generally, when we're reading a very complicated document, like an email, right? It's very, very rare for us to find these things together, right? It's very rare to find these structures where you have all these words occurring together in a certain order, correct? Do you guys agree that this is a problem? So don't you think this will always be zero? Don't you think this will always be zero? Because we may not have encountered that sentence anywhere. It's a new type of sentence, right? So generally, when we are talking about solving problems with joint probabilities, it's very, very important to understand that the probability of seeing these words in exactly the same order is going to be very low. Okay, it's going to be very low. So instead, we solve this problem using a few strategies. Okay, now let us talk about the strategy which Indradeep and Anil have put forward. Right? Okay, and Deepit also actually. Deepit also has mentioned this. Let's take that and understand this. So the problem here is that I don't know this one. Probability of word 1, comma, word 2, comma, word 3, comma, so on till word n. Right? The most naive way of solving this is by saying this is nothing but P of W1 into P of W2 into P of W3 into P of W4 into all the way up till Wn. Right? And this is nothing but naive Bayes approach. What is the assumption here? All word occurrences are independent of the others. Okay, cool. So now let us stop here and analyze this. Okay, let us say I have a corpus which contains a lot of documents about cats. Okay, I have a corpus which has a lot of documents about cats. Okay, but now the sentence that I'm writing in an email could be something like my dog dash, right? My dog dash. Now here is the problem. Because my corpus has cats, it may not be possible for my model to correctly predict this. Right? It may not be possible for my model to correctly predict this because the probabilities that I have learned is from cats. Right? The probabilities that I've learned is from cats. So now what do I do here? Right? What do I do here? Or to take a different example, to sort of point out what the problem here is, let us say in this cats, let us say we take this corpus and we find the most commonly used word is the, right? The most commonly used word is the. So let us say, don't you think that if I'm just going to assume this, it is always going to be the, right? Don't you think it's likely that my model will try to predict the word the many times, right? This is essentially the problem with assuming that all of them are independent of each other. Okay? This kind of an approach, a naive Bayes approach, where I assume that all words are independent of the other, they will actually fail to capture any contextual relationship between the words. Right? Do you guys agree that this is a problem? Do you guys agree that this is a problem? First of all, do you see the problem? Only one person agrees? Guys, am I teaching one person or many people? Okay, 3 people agree. Fine. In a class of 25 people, 3 people are listening. Okay, more people are listening. Okay. Sorry guys, it's a small class, so I want it to be more interactive, right? I'm really sorry if that disturbs you, but I want this to be interactive. Okay, cool. Moving on. Here is the issue. If we simply apply naive Bayes approach, we will run into trouble. It will simply start taking the most frequent word that it encounters and it will keep predicting that. Won't really help us with anything. Okay. So what do we do here? What do we do here? Can we use a concept we learned last class to solve this problem? Any concept from last class which solves this problem? I'll give you a hint. In last class, in the word2vec library, right? In skipgram, yeah. Use a small window. Perfect. So Vishwarup and Indradeep have given me the correct answer actually. So what we can do is we can use a small window which captures the context. Okay, small window, skipgram, both of these are correct answers. I was actually looking for the keyword ngram. Yeah, Sumit has given me that keyword. Perfect. So if you remember last class when we were building that word2vec using the library, right? We had specified one ngram parameter there. So that ngram basically told you what window size should I look at so that I can keep matching words together, right? So that is the idea now. So the naive Bayes approach basically will put everything like this. Now what we're going to do when we use ngram is the following. Okay. So the solution to this problem of just giving you the most frequent word all the time is now going to be the following. So this is approach 2. Instead of writing this conditional probability P of W1, W2, W3, all the way up to Wn, instead of writing it this way, what I'm going to do is I'm going to say this is not equal to P of W1 into P of W2. Okay, so let's break this down. In fact, let me just break this down. Let me give you a simpler example. Let us just assume that there are 3 words over here. Okay, so naive Bayes. So A is naive Bayes approach. This will naive Bayes will tell us that this is P of W1 into P of W2 into P of W3. But the approach we are now going to take up, or the example I'm now going to tell you, is that of a bigram. Right? The idea behind a bigram is, if I have a sentence, like let's take an example sentence, right? The man saw a girl looking through his telescope. Okay, so there is a man who's basically having a telescope. He's seeing the girl looking through that. What we can do here is we can try to capture the dual, like we can try to capture the relationship between 2 consecutive words, right? We can set a window over here, right? If I want to take 2 words at a time, we can basically set a window here like this. So the man is one possible pair. Then we have man saw as another possible pair. Okay. Then we have saw as another possible pair, and so on, right? So we have these pairs. If I have to now convert this to my math notation, how will I do this? I have W1 here, W2 here, right? Then I have W1 here, W2 here. Then I have W1 here, W2 here in this pair, okay? Notice that W1, W2 I am setting based on the pair, in the order in which they're appearing. I'm not setting W1, W2 for the whole sentence. I'm extracting pairs from this sentence and I'm setting them as W1, W2, okay? Now, what I can do is I can use this idea now to break down this conditional probability in a slightly different way. Okay, I can use this concept to break down the conditional probability as follows. I can say P of W1, W2, W3 is equal to P of W1. So one moment. The third word will come first, right? Yeah, my bad. This will be W3, right? Yeah, W3 given W1, W2 into P of W1, W2, right? Is it okay if I break it like this? Do you guys agree that this right hand side over here is equal to the left hand side? Yes, right? Why is this okay? Because I am now clubbing W1 and W2 as an event A. I'm clubbing W3 as my event B, and I'm simply using this formula. I'm simply using this formula that I had over here, right? I'm simply using the conditional probability formula that I have here. A is nothing but W1, W2 together. B is just W2. Okay. So now I'm sending that W2 on the other side. Okay. I'm sending it to the other side. And that is what is giving me this P of W1, W2 in one part and P of W3 given W1, W2 in the other part. Okay. So this way of breaking it down is actually a trigram, guys. I'm really sorry. This is an example of a trigram, not a bigram. When I have a window size of 2, right, what I have to do is I have to further simplify this. Okay, so let's do one thing. Let me continue with this expansion and show you how to get to the bigram part. Okay, so now what I will do is I will say that in this part, let me ignore the effect of W1. Okay, I don't care about W2, right? I don't care about W1 when I'm looking at W2 over here. So what I can do instead is I can write this as P of W3 given W2 into P of W1, W2, right? And now this again I can split it further. I can write this as P of, so this term I'm going to simplify as follows, right? I'm going to simplify this term as P of W2 given W1 into P of W1, right? So this is how I'm breaking down this conditional probability into these pair forms, right? So this is how I will simplify my conditional probability into the appropriate bigram representation, where I basically have one pair. I basically have now what is the probability of W3 given just the first 2 words. So let us now try and understand this problem. If I just give you the words the man, okay, and dash, okay, you will now go and you will look at all possible bigram probabilities. What are bigram probabilities here? The probability of word 3 given word 2, right? Or the probability of word 2 given word 1. Using these bigram probabilities, the maximum over there is what you will fill over here. So you will look for that word which will give you the maximum probability given that the previous word was man. Okay, and that is how you will fill it here. Correct? Okay. So if this math was too complicated for you guys, let us take some actual examples and let us solve the actual examples. Okay. So I'm pretty sure some of you got lost in the way I was simplifying this. I was applying probability theory here to simplify it. If this is confusing you, let us go and see some examples that will make it very clear. Okay. So let's go see some examples. Okay. So all of this is something we have discussed. Let us now go to the n-gram models. Cool. Deepit says, we did not get why you ignored W1. Deepit, you remember you were ignoring W1 over here. This is independence assumption, Deepit. If I want to ignore something over here, I just have to assume that W3 is independent of W1. Remember independence from our probability theory? It is this, right? When do I say A and B are independent? Let us recollect that. This is a good question actually. I just want to make this clear for everyone. A and B are independent if P of A given B is equal to P of A, right? So the information that B has happened gives you affects the occurrence of A in no way. That is when we say they're independent. So that is why we have this. Cool? Yes. Okay. So let's go ahead with this, guys. Let us take the n-gram models and let us look at this. So Indradeep's question is, so when we refer to just the previous word, then it's bigram. When we refer to previous two words, it's trigram. Yes, Indradeep, that is how it is. So why is this notation coming? Why is that n-1 thing coming, right? It's because look at this. To make a bigram, I need to form word pairs. So that is where that bigram is coming from. So that is why to predict the next word, I just need one word before. That becomes bigram. If I'm taking three words, then it becomes trigram. So that way. Okay, cool. That's a nice question though. Even I used to have that doubt. So yeah, like that bi and tri is actually n-1. So that thing was there. Yeah. Okay, anyway, let's continue. Let's now study n-gram models. Okay. So guys, the n in n-gram basically tells you how many words should I take and form pairs before I can compute these probabilities. Okay. Very simply put, if you don't want to understand the math, what you can think about this, the simplest way to think about it is n-gram, okay, the word n-gram refers to how many words, sorry, not how many, n words are n word windows, okay, or let me make it simpler. A window size of n is selected to calculate the probability. Okay, a window size of n is used to calculate the probability. That means n-gram. Okay, so for example, bigram is when we use 2, trigram is when we use 3, and so on. Okay, so largely speaking, guys, the computational complexity increases a lot with this n, right? You can think about it, right? Don't you agree that if I start taking n to be a very large number, I will have to consider a very large window size to compute each probability. So the computational complexity generally increases when I increase my n. So typically what people do is they stop at around 3 or 4. Nobody really goes beyond 3 or 4, and that is what we do, right? This is a little bit like your arima or sarima with look behind, like the look behind of 3 or 4, something like that. So we are already doing some kind of time series analysis over here. It's kind of similar to time series analysis, right? Okay. So moving on. Very simply, n-grams are essentially a sequence of n words or tokens. 1 gram or unigram is 1-word sequences. 2 gram or bigram is 2-word sequences. And 3 gram or trigram is 3-word sequences, and so on. Okay. So how do they work? They work as follows. If I have a sentence, if I have this joint probability, right? This joint probability is exactly what I'm calling the probability of the sentence. Okay, probability of I being the first word, have being the second word, being the third word, and dream being the fourth word. This probability term is now going to be P of I into P of have into P of A into P of dream. If this is the case, which one is it? Uni by try. Which one is it? 1, 2, 3. N is 1, 2, 3 for this one. Quickly, can somebody tell me? What is N for this approach? This is try? No, guys. Guys, come on, come on. We just saw this. We just saw this. If I have P of W1, W2, W3 all the way up to Wn, if I break it down like this is 1, right? This is unigram. There is no conditionality coming here. This is 1, guys. This is 1. Okay. P of I have a dream being P of I into P of have into P of into P of dream is unigram, because I'm simply taking the probabilities of each individual word and I'm multiplying it, right? So this is a unigram, guys. Sorry for the confusion. Is everyone on the same page? I see that a lot of people gave me this answer, right? Guys, is this clear? This is unigram. Anyone who has a doubt, please hit no right away. Okay? Hit no if you have a doubt why this is unigram. Otherwise, I'll proceed. Okay. Nobody seems to have this doubt. Let's proceed. Now let us see bigram case. In the bigram case, I will take 2 words at a time, right? So P of I have a dream will now become P of I given blank, okay? P of have given I into P of a given have into P of dream given a, right? This is the bigram thing. So here N is equal to 2. Similarly, P of I given dream becoming this. P of I given comma, like this is basically blank. P of have given blank, comma I. P of a giving I, comma have. And P of dream given have, comma a. This becomes the trigram. So essentially, the n-gram probability, breaking down the n-gram probability works like this. Okay. That is why I sort of wanted to construct here. Yeah. So Indradip's question is, what is P of I given blank? I'll tell you this, Indradip. I was just coming to this. Okay. Yeah. So now let us discuss this. Okay. Let us say I want to now apply a bigram. Okay. Let us see this issue of bigram when the user has not inserted anything. Okay. Let us say that this is the user's window. Let us say the user's cursor is over here. Okay. Remember, our user is writing an email. We are trying to solve the problem of predicting the next word in an email. Okay. Let us say a sentence has gotten over. So I have 3 books with me. Full stop. Right. So let us say the user has written such a sentence and now the cursor is over here. Okay. Remember, guys, this is the start of a new sentence. So I cannot really use anything from the previous thing to start something here, right? So what should we do in this case? Can I really apply bigram here the way we have just defined it? Can we apply bigram here? The bigram strategy breaks down, right? Yeah, we cannot apply bigram here. We cannot apply bigram here. So how do we solve this problem? Did you guys come across this problem when we were encountering naive Bayes? Yes. So Indradip has given me the solution, but I hope the others are following. Okay, guys? The strategy to deal with this problem is we are now going to introduce a new token. Okay? New token, which basically represents the start of the this thing. So let me call this start. Okay? The start is a new token. New word we are using to mark the start of the sentence. Okay, let's see how to use this. Let's see how to use this with an example. Okay, cool. Let's see how to use this with an example. So guys, the concrete example we're going to use to sort of understand this uni, bi and trigrams is this corpus. Okay. How many documents do I have in this corpus? Quickly. How many documents? 3 documents, right? Okay, cool. How many words do I have here? Let us count. Okay. Guys, I told you that start is a new token, right? Start is a new token. So remember, you have to count the start also. Okay. So I have 1, 2, 3, 4, 5, 6, 7. I have 7 tokens over here in my first sentence, right? In my second sentence, I have 1, 2, 3, 4, 5, 6. 6. In the third sentence, I have 1, 2, 3, 4, 5, 6, 7 again. So 7 twos are 14 plus 6 is 20, right? So the total number of words that I have in my corpus now are 20. It's not the unique words, guys. Remember, I'm not asking you the unique words. I'm saying how many total words do I have in my corpus. I have 20 words over here. Why am I saying this? It's going to be very useful in calculating probabilities. Remember, denominator should be sample set. Remember that, right? So the denominator should actually be the total number of words, not the this thing. Okay, cool. So now, using this information, let us derive what should the unigram be for this. Okay, let us derive what the unigram should be for this. So the unigram model for this corpus is going to be as follows. I'm going to say start, the word start. See, now in unigram, what is it that I have to do? Remember, in unigram, all I have to do is I have to take the individual probabilities of these words. I only have to care about the individual probabilities, right? So if I'm just caring about the individual probabilities, I have to first create this data structure called count table, which is going to have the individual probability of each word. The denominator is 20 because there are 20 words in this corpus, and the probabilities are going to be as follows. Start has appeared 3 times, so start is going to be 3 by 20. I has appeared 3 times, so 3 by 20. Want has appeared 1 time, so 1 by 20, and so on. Okay. Now we will keep this data structure in our mind, and when we are predicting the next word, all we are going to do is we're going to select the word which has the highest probability and return that, right? Any problems that you notice here? We have multiple words with the same probability. So we have to apply some sort of technique to resolve this, right? Maybe we can do something like just select one of these words which are equiprobable randomly and return that, right? That is one strategy to do. But this becomes an issue with unigram models. So generally people don't prefer unigram models. It's not good enough. Unigram is generally not good enough. So nobody really uses this. But for the sake of completeness, let us see what this will look like. So in the unigram model, we have the individual probabilities like this. If I now want to calculate the probability of my whole sentence, I have to calculate the joint probability here, right? So this is P of I into P of have into P of A into P of dream, and that becomes a very small number if you see, right? This is one of the issues with probabilities. Moving on. Let us now see how to do the same task for a bigram model, okay? So in bigram, guys, if you remember, I have to start taking pairs into account, right? So now the data structure that I have to create will become a matrix, okay? So let us understand how to interpret this matrix. So every entry that you see in this matrix here, right, is the probability of seeing want given start has already occurred. So we are basically looking at the probability of the column name given that the row name has occurred before it. Okay, that is how we interpret this. So now let us see. Okay, so what is the most common pair that you see here? Can I try and see I have, right? Can we say that I have has occurred 2 times? Has I have occurred 2 times? Okay. And the total number of pairs that I can have over here is 17. It turns out that the total number of pairs I have is 17. So I have to look at I have. So I and have is 2 by 17, right? So the probability of have given I has already occurred is 2 by 17. That is what we are seeing over here, right? This is how we are getting this 2 by 17 here. Okay. Same way we can do for everything else. Are you guys confident enough that you can write code to do this? Are you guys confident enough? What data structure will you use in Python to implement this? Which data structure will be most useful? What do you think to implement this? I'm giving you 3 options: list, dictionaries, and sets. Dictionary, right? Okay, perfect. Dictionary will be the most useful because I can simply create a dictionary. Every time I encounter a pair, I can put that pair inside this and I can do it, right? Remember, guys, this matrix is going to be very sparse. So how do we deal with sparse matrices? We use dictionaries to represent them, right? So the hint over here was we have a very sparse matrix. If you notice, many of these entries are 0. So the dictionary will be the most efficient way of storing this data structure. Perfect. Cool. So Prasad, you're not wrong. Okay. So guys, in private chat, Prasad told me data frames. Data frames also are okay, but then it has that sparsity problem. So dictionary is preferable. Okay. Cool. So now, if I now calculate these probabilities and put it over here, this is what the probability table will look like. Okay. Cool. So now the probability of this sentence, P of I have a dream, is going to start looking like P of I given start into P of have given I into P of a given have into P of dream given A, right? So this is the way I can calculate the joint probability of this sentence given each of these words. Okay, everyone with me so far? Everyone with me so far? Guys, quick check. I just want to ask, is it okay if we take a 5-minute break here? We can take a quick 5-minute break, and once we come back from the break, we can continue understanding how to create for trigrams and so on, right? So we can do that. Cool. So before I go for the break, guys, there are a couple of questions I want to deal with. Then we will go for the break. Indradeep's question is word pair as key and max probability word as value should be the dictionary structure, right? Yes, Indradeep, exactly. Indradeep, you can check your answer. It's exactly what you said. It's exactly what you said, right? See, this will come on the row columns. Sorry, this will come on the rows and this will come on the columns. So that you're right. Yes. Okay. So once we come back, we will quickly see how to make trigram models, and then we will try and implement this using Python code and see how effective this is. Okay, that is what we'll do after the break. Let's quickly go for a 5-minute break and come back. So I will leave this over here. In the break, if you're interested, you could stare at this trigram that has already been created. And yeah, I'll see you guys in 5 minutes. And we're back. Can I get a quick confirmation if you guys are back? Okay. Some people are saying no. Nice. Okay, cool. I'm hoping two people are actually back, and I'm sincerely hoping the others are also back. They're just lazy to hit that yes button. I also feel lazy sometimes. It's okay. That's fine. But yeah, I'm assuming you guys are back, right? Quick correction. Indradeep, I'm really sorry. Before the break, I did not understand what you were saying. You're right. In the dictionary structure to implement a bigram, the word pair should be the key, and it's not the max probability that you store. You store the actual probability. So how I will construct a dictionary from this bigram, right, is I will see I comma I. So I will take start comma I. Okay, start comma I's probability will be the 0.176. So I will actually store the probability of seeing that pair in that dictionary. I will not store the max probability. I will store the actual probability. I will do the optimization later on. When I'm constructing a bigram model, I have to store the actual probability that I'm observing. And then on top of this, later on, we will do whatever it takes to do the prediction. Okay. Just wanted to clarify that. Hope it's clear now. Okay. Moving on. Let us now see how to go for the trigram model. Sorry, guys. Yeah. Let us see how to go for this trigram model. Now, here is a problem. Okay, when it comes to trigram, right, I require two words before the start of the sentence. So let's come back to this problem. Let's come back to this problem for trigrams. Okay, if for the same input, okay, my user has entered this sentence. I have 3 books with me, and now the cursor is over here. Okay, for the same problem, in the case of a trigram, right? In the case of a trigram, how do I solve this? My cursor is over here, okay? My cursor is over here. How do I now say what should the next word be in the trigram? See, for bigram, what I did was I put a start over there, right? I said P of word given start, right? But now I have to do something else over here, right? What do I put here? That is my question. What is the simplest solution that you can think of for this? What's the simplest solution? Can I not just put the start again? What do you guys think? Okay. Okay. Are you guys following this? Are you guys seeing the problem first of all? I'll explain again. Okay. My cursor is over here. I want to predict the next sentence. I need to find the maximum probability. Now, when I'm doing a trigram model, the conditional probability will look like this, right? Probability of word given start comma blank. So the question I was asking was, what should I put here? When I was doing bigram, it was probability of word given dash, right? I solved this problem by putting a start there. So I'm asking you now, is it okay if I just put another start here? Or should I use a separate token for this? What do you think? Who thinks start is better? Hey, say yes. Who thinks new token? Say no. Which is better? Okay, new token is better? Perfect, right? Okay. So generally, putting a new token to indicate that this is the first word is kind of better in the trigram model. But what people do is they go for this one. They go for this start comma start. They simply repeat that. Okay. They simply repeat that. Reason being, it will not make so much of a difference because generally people don't look for predictions here, right? So if you're thinking of this as a system, it's okay to use both. But if you want to really build a powerful system, it's important to look for a different token over here because the state of being the first word and the state of having two starts is totally different, right? So because of that, it's better to use a different token. But for now, we will solve this problem by simply putting a start there and we will move on. Okay, cool. So now when I want to construct a trigram for this corpus that I have, this is how it will look like, right? So I have start comma I over here, and then I will see the probability of start given start comma I, right? Things like this. So I think this is a mistake. It should have been start comma start over here, and then this should have been an I. Cool. I'll get this fixed maybe later. But yeah, essentially what I'm trying to say here is now when I'm constructing a frequency table for my trigrams, I have to look at what are the two words which came before, and then what is the probability of finding this word after those two words came, right? So I look for all kinds of pairs over here. This is by no means an exhaustive list, okay? I look at all the pairs here and I look at all the words here, and these are the probabilities that I have for each of these. Okay, cool. So the probability table will look like that. And when I'm predicting the probability, or when I'm looking at the overall probability of a sentence, this is how I will do it, right? I will say P of I have a dream is P of I given start comma start. So this is where I'm applying that idea, right? I'm simply going to put one more start here into P of have given start comma I into P of A given I comma have into P of dream given have comma a. Okay, so this is how I will build the probability of my sentence, and that is what I will get. Now the question is how to build an n-gram model that will learn word probabilities using this thing, MLE, right? MLE is maximum likelihood estimation. So the idea is very simple, okay? The way you implement this is you simply implement a way to get this table. Generally, what people would prefer is to put a dictionary implementation there for the reasons we just discussed, and we will go ahead with that, right? So briefly, let us see how we will train that. So given this sentence, we will basically, calculate all of these probabilities. In the unigram assumption, the probability of each word is independent of any words before it, right? So this P of have given I, P of a given I have, P of dream given I have a, all become just P of this thing. Remember, the independence assumption allows us to get rid of stuff which is coming after the given symbol in the probability. So all of these probabilities in this case will simply become individual probabilities of the words, right? So P of train, P train of dream given I have a becomes simply P train of dream. So this is going to be nothing but number of times I've seen dream in my corpus divided by the total number of words in my corpus. Okay, this is what it's going to look like. How do we evaluate this model now? If I have prepared this model, I have to now be able to evaluate how good this model is. What is the level of understanding that this model has captured, right? Generally, when we build a model, we want to see how good it is. So how are we going to do that? Let's see. So the way we generally evaluate the model is we start looking at the probability of sentences, okay? We start calculating the probability of the sentence. So the probability of I have a dream now is going to be this whole probability, okay? And then what we do is we compare this probability of the sentence with some score of how important that sentence is in the whole document, okay? So there are some ways of doing this. You can either use something like TF-IDF to determine the importance of that whole sentence, right? You can use TF-IDF very easily. You can use something like can you use any word? No, you can't. Okay, so TF-IDF is generally how you do it. You can use any other strategy which you use for encoding documents in a corpus, right? Any of those strategies would work. So that is how you evaluate the goodness of your model. Okay, cool. So the calculation is kind of straightforward. So I'm going to skip this. If you notice, it's simply whatever we have been discussing so far. Okay. So now the question is, how do I now use this guy, the unigram model, to evaluate a bigram model, right? So generally what people do is you can use this evaluation technique, right? You can either compare this probability to that of a, you can compare this probability to a TF-IDF, or you could compare it with that of a bigram model, right? Or you could sort of use it for a trigram model. So the idea is you can use the probability of these sentences with respect to bigram, with respect to trigram. You can compare these internally and get the evaluation, or you can compare it with the TF-IDF score of your sentence within the whole corpus. And that will give you an idea of, has my model actually learned to recognize the important sentences in my corpus and make predictions based on that, right? That is our ultimate goal. We want to give predictions in a way that it's actually useful to the user. Cool? Okay. So now that we have done this, let us sort of generalize this for an n-grams. So the idea is the same. What I will essentially do is first calculate all these probabilities that I want, the conditional probabilities that I want. Using this, I will once I have evaluated this, I will go and take my corpus and I will see the importance of each sentence through this strategy, and I will compare it with either TF-IDF or I will compare it with a different size, different n-gram size. Okay, and that is how I can evaluate the goodness of my model. Okay, there are some obvious problems, right? This is where we go back to the problems with probability values. Okay, so we had just discussed this. We had seen that there are some typical problems with probabilities. The problem is that these numerator and denominator terms could be very small, right? So the way we were solving that was by using log probabilities. Another way was this probability of how to deal with unknown words. So both of these strategies, let us look at it really quickly. So the probability will be very much less, close to zero, if the text length is big, right? So does this tell you something about the predictive power of our model? Do you think our model is more likely to recommend short sentences or long sentences if we use this evaluation method? What do you guys think? Will it favor short sentences or long sentences? Obviously, it will favor short sentences, right? It will try to give you suggestions based on the shortest sentence it can make given your prompt. That is the problem with this. So generally, we have to sort of take care of this problem where we sort of equalize the probability of the more important sentences, which could be longer, right? So the way we do that is we go for log to do it. So the gap between long sentences and short sentences are reduced. So now it will try to give you an optimal length sentence. It will not try to make the sentence too long. It will not try to make the sentence too short. When we start applying log probabilities to evaluate our model and decide which one to use, right? So this is kind of an important concept. The way to fix this problem, the bias towards shorter sentences, is to use a log probability term to evaluate your model. Okay, cool. So with log probability, it kind of gets simple, right? If you have the product of many probability terms, if you apply log, it becomes a sum. So whatever used to be product of probabilities will now become sum of probabilities. You simply take the sum of log probabilities and you divide it by n. Okay, cool. So this new term that we're getting on the right hand side after applying log is called the average log likelihood. Okay, it's called the average log likelihood. Can you guys tell me something? Does this look very similar to something we've seen before, the right hand side? Have you seen this form somewhere in classification or something? Is this form familiar to you? Okay, I'll give you a hint. What if the probability of all words I assume to be 1 upon n? Log loss, right? Perfect. So this is log loss. Actually, the keyword I was looking for, guys, was categorical cross entropy loss. So this term, right? This term on the right hand side is also known as the cross entropy term. Okay, this is the cross entropy term. Then you assume that the probability of each word is the same. Under that assumption, the term on the right hand side becomes the cross entropy between a uniform distribution and the distribution of the words in your sentence. Okay, that is why this sort of makes sense. We will see how this makes sense shortly, but I just want you to remember this looks a little bit like the cross entropy loss, and that is why this is what is used to check whether our model is good or bad. Okay, that is the intuition behind this math formula. Okay, cool. So of course, cross entropy is one more evaluation metric where you sorry, my bad. There is one difference between this and cross entropy. You have to take a negative over here, right? Cross entropy is the negative version of this. So my bad. It is not exactly cross entropy. You can get to cross entropy by taking the negative value of this, and then you can use that to evaluate your method. Okay. And finally, there is another way of evaluating your method, which is known as perplexity. And this is nothing but the exponential of your cross entropy. So if I take this term and I calculate e to the power this of each of these terms here, right? That is going to become my perplexity. Another way of looking at the same thing, right? Another way of looking at the same thing is you can define perplexity to be this formula. Okay. So if we take this formula and we apply e to the power something over here, it will simplify to this format. Okay. The 1 upon n over here will now become an under root, right? It will be 1 upon nth root of this whole probability term. And since it is negative, that will come in the denominator, which is why we will have the nth root of 1 upon p of wn, w2, w3, all the way up till wn. Okay. This is what we call the perplexity. And the perplexity is what we can use to check whether our model is doing good or not. Okay. Cool. So the question here is, should the perplexity be low or high to check whether a model has understood something, right? That is a valid question to ask. should my perplexity value be low or should it be high to check my understanding of my model? Okay. It turns out that lower the perplexity score, higher is the model's understanding the language. Why is this the case? Because if my model is able to say this sentence is making a lot of sense, the perplexity of that will be low. And that is why a lower perplexity score means that the sentence is more probable to happen or more probable to occur in a body of text. Okay. So you can reason this out by studying this formula. But hopefully this is very clear from the context. Average log likelihood, if it is higher, exponential of that will be lower. So a low perplexity score will tell you that the model's understanding of the language is very good. Okay, this is how we essentially use perplexity to check whether our model is doing well or not. And of course, there is the obvious way of checking whether your model is doing well or not. You can just give these short prompts and you can see if it is giving meaningful results. That is one more way of doing this, right? So that's another way of doing the same. And cool. So now we have covered how we can evaluate whether our model has learned something or not, right? We can simply calculate the perplexity score. If this perplexity score is something, it's a number which is much lesser than 1, then we say that our model has learned something very well. If this number turns out to be greater than 1, then we say that our model has not really learned well. It is doing as good as a random guess, right? It's doing as good as a random guess. So comparing the perplexity to 1 is how we do this. Once we now go through this whole thing, let's come to the second problem that we had encountered, right? Which is what to do with words which do not appear, right? How to handle words which we have not encountered in our corpus. So the way we handle this in the math is we can use Laplace smoothing. Okay, Laplace smoothing. Let me explain the concept of Laplace smoothing. So the basic problem is explained over here. The number of times you have seen the word which you have not encountered is 0, right? So probability of that is going to be 0 upon n, which is 0. So when you are calculating log of 0, you'll get minus infinity. So minus infinity is no way to check anything, right? Like we can't really interpret minus infinity as anything. So the way we solve the problem is we introduce this artificial unigram called UNK. The UNK basically means it is an unknown pattern that we have encountered, right? So this is an unknown pattern. So we basically say all the unknown words will fall under this category, which is known as UNK. Okay. Once we define this, we will form a special place in our matrix, right? Our unigram, bigram, trigram matrix, which we were making over here. We will have one special place for it over here in this table, just like we had for the start and end, right? Just like we had for start and end, we will put a special place for that unknown, and we will keep including that probability over there. We will update that in a special way. What is that special way? Let us see now. Okay. So let us discuss how to apply Laplace smoothing to solve this problem. Basically, the idea behind Laplace smoothing is you will go and you will increase the frequency of all your words in your corpus by k amount. And that is why, because the minimum value of the probability for all the words in your corpus is k, the unknown words probability is now going to be k, right? The probability of that is going to be k upon n. So once you do that, right? So see this. So p train of unigram, where your unigram is unknown, is nothing but n train of unigram plus k, and your denominator now is going to be n train plus k times v, where this is v is the unigram's vocabulary size, right? Once we have this kind of a structure, we will use this to figure out what our unigram is. So the problem of having 0 probability for an unseen word is now fixed, because by default, the probability assigned to an unseen word is going to be k upon n train plus kv, right? So this is how we solve the problem of not seeing. So this is how we solve the problem of dealing with unseen words or calculating the probabilities of unseen words. And this is essentially what we get. So this method is known as Laplace smoothing. So this has been taught as a part of your naive Bayes this thing, right? This has been covered as a part of naive Bayes. Okay. Some people are saying no. I see. Okay. Right. The people who have not seen this before, can you tell me, is the intuition of this clear? The intuition is very simple, right? See, okay. Okay. I'll just repeat the intuition for clarity's sake. Okay. Let's go back to our table and let us see what the problem is over here, right? The basic problem here is we have these zero probabilities in a lot of places. We don't want these zero probabilities because it will cause problems for us. So the way we deal with it is we will increase artificially the probability of all the words by k amount, and we will say the probability of an unseen word is going to be k, right? So that is how we are basically dealing with this problem. Okay. Yeah. So once we do that, there are certain problems with this. Yeah. Yeah. I see, Vishnu. Okay. So this is how we deal with unseen data using Laplace smoothing. The alternative, right? The alternative to using Laplace smoothing is we can use something which is known as k smoothing. Instead of increasing the count by k for each word, we can increase it by a fractional amount, right? So if you simply take this k and instead of making it an integer, you make it a number which is smaller than 1, then it becomes k smoothing. Okay, that is what k smoothing basically is, and we can use this to sort of work with things. Another very nice technique for dealing with unseen words is something which is known as back-off and interpolation, right? So the point of back-off and interpolation is if we have a probability of a trigram like this, right? If we don't know the probability of the trigram, we will simply remove one thing from here, and instead of using the trigram, we will use the bigram probability over there, right? So this is what back-off and interpolation means. If there is a probability while I'm making my trigram table, I'm not able to see that pair occurring anywhere, I will simply take the bigram version of it and use it in its place, and that will give me the probability that I should use while I'm doing my predictions. Okay. So this is what we call back-off and interpolation. Of course, you can weight these probabilities in a certain way. You can apply some weighting over here, where lambda basically tells you how much importance I should give to this versus how much importance I should give to this. If we use these kinds of techniques, we can deal with unseen pairs, triplets, quadruplets, and stuff like that. Okay. So broadly speaking, this is how we deal with unseen pairs, triplets, quadruplets, and all those things. And this is a viable technique. There is one technique which we have not yet discussed so far. Do you think it's possible for us to update our table every time we see an unseen word? Does that seem like a sound strategy? What if an unseen word comes, what if we update our vocabulary and we go and recalculate all our probabilities? Do you guys think that's feasible? That seems like the most intuitive way to do it, right? Why not? Why not? If I was okay, so let's give me I'll give you an example. Okay, let us say we are deploying this model to suggest words for you when you're typing SMSs, and of course there is no way for people to know what your name is, right? There's no way they can go and get all the names of all the people on earth. Okay, so let us say the most common thing after you say regards, right? At the end of a message, typically you say regards followed by your name, or thanking you followed by your name, right? So for that prediction, how can you pick up new words, right? So the best way to deal with that is to actually go back and recalculate all your probabilities and update it there, okay? And this is what's actually done in SMS systems and on your phones, okay? So it actually learns your name and it learns these common words on the go. It will maintain one version of probabilities, and as and when you keep typing your SMSs and as and when you keep interacting with the app, in the background, it will keep updating its probability table and it will keep updating the rules using which it is able to do these predictions, right? So that is one viable way. It does take a lot of computation, but if you are able to implement it effectively, it is the best possible solution. That is one way for you to guarantee that even if the model has not seen a word before, it can learn from the user and it can predict that word later on. Right? It will seem like a very intelligent system if you implement it that way. So that is one valid way of doing things if you don't want to use any of these methods, right? Okay, cool. So which method do you choose and why? It really depends on the type of ambiguity. So there are certain ambiguities which are defined here. Let's go through them quickly, right? So let's look at the different types of ambiguities we commonly encounter. We have lexical ambiguity, where there is ambiguity in a single word. For example, the word silver could be a noun, adjective, or a verb. So if you guys have seen this TV series called Cobra Kai, or if you've seen this movie called Karate Kid, right? There used to be one character called Terry Silver. So over there, silver appears as a name. Whereas the word silver is, of course, the metal which is very precious to us. That is also a silver. And then you can use silver as a color to describe something, right? So those are the three cases where silver could mean multiple things, right? Then you have syntactic ambiguity, where the man saw the girl with a telescope. What does it mean? So does it mean that the man saw a girl who was holding a telescope, or was the man looking through the telescope to see the girl, right? This is syntactic ambiguity. We don't know with a telescope refers to girl or man. Okay. Then you have semantic ambiguity, where meaning of the words themselves can be misinterpreted. The car hit the pole while it was moving. So if we read the sentence carefully, it's obvious that the car is moving, okay, because it hit the pole. So the car is definitely moving. The question is the pole moving? So while it was moving, does this it refer to pole or car, right? Maybe the it refers to car because it's the most obvious choice, or it could be referring to the pole. So these are semantic ambiguities. Then we have anaphoric ambiguities, where we have the horse ran up the hill, it was very steep, it soon got tired. So the word it over here in this sentence refers to the hill, but the it word over here refers to horse, right? Can you guys tell me, if I'm using a trigram model for this and I stop over here, it was, right? If I stop here, it was. Do you think a trigram model can figure out what it should fill over here, right? Can a trigram model figure out whether I should talk about hill or should I talk about horse? What do you guys think? It cannot, right? So this is what I mean by long range contextual dependencies. So all these problems that we are having here, right? All these ambiguities that we are having here, these ambiguities are existing because there is no context for these sentences. So if I stop over here, it is very, very unlikely that my model will predict this format. Okay. So the point is this, the whole point of discussing all these ambiguities is bigram, trigram, n-gram models in general cannot figure out what to predict because they don't have such high contextual information, right? We cannot construct models which are more than n equal to 4. N equal to 4 can at max capture the context with 4 words. So if you were talking about a horse like 7 words before, right? There is no way that the model will know that we should talk about the horse and not the hill over here, right? That is the problem that we're talking about here. Yes. Okay. So this is actually the limitation of n-gram approach to language modeling. Contextual information like long-range dependencies are not able to be captured through the n-gram model. To solve this problem, we'll have to actually wait till we come to transformer models. The whole reason why ChatGPT is able to give you very, very confident and good sounding answers, right, is because it is able to remember the context it has talked about 3 sentences back. So to build the context, you have to give it more hints than just the previous few words, right? Even RNNs will suffer from these problems. Okay, long short-term memory will also suffer from this kind of a problem, but BERT-like models will not, and we will see how those perform later on, right? Okay, so we have now seen everything that we need to see to sort of build this solution. So guys, now for the next 15 minutes, let us quickly discuss the code to actually solve the problem. Okay, quick reminder, what is the problem that we were trying to solve at the start of the class? We were trying to build a word completion thing, right? Sentence completion kind of system. So now let us actually go and solve this problem using whatever we have discussed so far. Okay, cool. Before I start discussing the code, any doubts up to this point? Like any doubts, any confusions, any concerns? I'll pause over here. If not, we can now start discussing the code implementation of our strategy. Okay, cool. Okay, so I see that there are no doubts. Let's continue. The main two libraries that I'm going to be introducing today are these two. Okay, so we have this email library which is used for pre-processing email data. So guys, generally when we send emails, right, the metadata is very fixed. Like you will have to, from, timing, and re, and reply and forward, FWD, all those kinds of things will be there, right? That will be the header data in your email. What this email library will help me do is it will help me remove all the unnecessary information associated with an email. So it will help me just keep the body of the text. right? Because that is what we want. We want to make predictions using the body of the text. So this will help us keep just the body of the text when we are making our prediction model. Okay. The next thing that we're going to introduce is this library called Word Cloud. Word Cloud is basically a library which is used for visualization. It will help you visualize which are the most probable words in your corpus, right? That is what we're using. And the rest of them we have seen at some point or the other. Like the rest of the imports is something we've seen at some point or the other. Let me just quickly check once. Is there anything? GC is garbage collect in Python. Anything that we have not seen doesn't look like it, right? We've pretty much seen most of this. So now let's proceed. First thing, of course, we're going to do is download our data. There is this data which is in the form of email.csv. What I'm going to do is I'm going to pd.readcsv this and see what this looks like, right? So my CSV file basically has two columns. It has the file column. This refers to the file where this email is stored. And then we have the message. So guys, notice this message ID, so much number, java.mail, whatever. This is the metadata that I was talking about. If we start building models with this, right, don't you think it's highly probable it will always predict this message ID because it's always going to appear, right? So it's always going to try and predict things like this. So we don't want this. We have to get rid of this. Okay, we have to get rid of this before we go ahead with solving the problem. So that is why we are going to use the email library to do that. For now, let us see the shape of our data frame. There are 181,000 emails in this data set. So there is no lack of data as such, right? We have no lack of data. Let's sort of look at an example of this data set. So here we have message ID, blah, 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 from so and so person to so and so person, all that, and origin. So the actual text of the email starts somewhere here, right? Somewhere over here it starts, the actual text of the email. So essentially, this is what we have to extract from this message. And this is what we'll be using the email library for. So I basically have body of messages equal to, so see this, right? This line is doing that, getting rid of all the extra stuff. E is equal to email.message from string message. So this message from string is a function in this email package. It is used to eliminate all this additional metadata. Once we do that, see what the content looks like, right? Bill saying thanks for the info I also spoke with. So exactly where we said that it should start, that is where it is starting, right? So it's picking up the body of this text from here to somewhere here, right? Somewhere here. It looks like it's somewhere here. Yeah, somewhere here. So this is what it means. This is what that email thing is doing. So from now on, whenever we're trying to build our model, we're going to use the content column over here to build our model. Okay. Now, once we start processing this content, let's see what additional processing we have to do in our processing pipeline. We'll first remove all the non-alphabetic characters and we'll convert everything to lowercase. Okay. And we'll remove extra space from the beginning and end from all our texts. Do you guys notice one step that I'm not doing over here? What is one step I'm not doing over here, which I typically used to do for the vector parts? Anyone can guess? What am I not doing over here? One important step. Stop words. Yes, Indradeep, exactly. Stop words. Can you guys tell me, should I remove stop words? Don't you think it will make my predictions very weird? I will never have an email which predicts the, right? Whereas the could be the most common thing it should be predicting. So maybe our life will get much easier if it keeps predicting the and we keep pressing tab, right? It will save a lot of time for us. So removing stop words will actually be counterintuitive for this application. Okay. So that is why we are not doing it. There's a good reason for it. Okay. Moving on. Now that we have done all this pre-processing to the stuff inside our content, we can apply tokenization and basically start training this model, right? By training, what I mean is building that dictionary or building the data frame or the data structure which is storing the probabilities for the pairs or the triplets or the single words that we are seeing. Okay, so starting from this point, we're going to start implementing that code. So let's see. First, we're going to do tokenization. Tokenization means simply taking your sentences, breaking it into individual words. So once we apply tokenization, look at this body list. So all the individual words become part of this list, right? This is what we mean by tokenization. Once we do that, we can see what our data set looks like. We're doing some exploratory data analysis over here. First thing we're going to look at is what is the length of our emails. Okay. So as you can see, the length, what we have plotted here is the frequency and the length of the text, right? So this bar basically represents how many emails are close to zero. So there are quite a few emails which have empty bodies. Okay, quite a few emails which have empty bodies. And as we keep progressing, as the text length increases, we have fewer and fewer emails. So from this graph, what I can say is I have very few emails which are 12,000 words long, but I have a lot of emails which are kind of short, right? Which is expected behavior. We typically don't want to send long emails unless it's like we're sending documents or something like that. So this kind of a distribution makes sense to us. What we can do to further visualize this is see the percentiles, right? So interestingly here, the 50th percentile is 687 words, the 90th percentile is 3000 words, and the 100th percentile is very, very large, right? What does this tell us about our data? What is the most obvious interpretation over here? Can I say that my data has a lot of outliers? Can I say that? Like all of these that I'm seeing here in large quantities, can I say that these are outliers? What do you guys say? I can say that, right? Because 90th percentile is 3200, but from 90th to 100th percentile, I have email lengths which are very, very high. Okay. So the takeaway that I'm going to get is I have a lot of outliers over here. So I have to keep that in mind. Cool. Little bit more EDA. So guys, this is where we are going to use word cloud to visualize what are the most commonly occurring words in our corpus. Okay. So this cell basically allows me to print all the most common words in my corpus. So internally, guys, word cloud actually stops printing stop words. So it will get rid of the most obvious ones. So the most obvious ones are going to be the and stuff like that, right? The good thing is word cloud allows us to tell it to not print the stop words because this is going to be obvious. We want to see what are the most frequently occurring meaningful words in our corpus, right? So it's important to sort of give stop words equal to stop words over here. So that is the only thing you need to remember when using this. And yeah, so we have this kind of a plot. Can you guys tell me by looking at this, what is the most commonly occurring word and does it make sense? What looks like the most commonly occurring word? Is it forwarded? Forwarded, right? So it makes sense. If you're forwarding an email, the word forwarded will appear there, right? So the word forwarded kind of makes sense. And looking at some of the other words which are commonly occurring, we have thank you, like thank you wala thank, then we have original, then we have message, then we have etc. Okay, I'm not sure what HOU means, but okay. But yeah, we have all these commonly occurring words, right? So this is a very nice way for us to visualize the most frequently occurring words in our corpus. This will be useful if you are solving a case study or something. So maybe keep this in mind. And yeah, so once we're done with this EDA, let us sort of see what are the most frequently occurring words. So these two cells basically gives us a frequency dictionary. Let us sort of go through it. Obviously, the most frequently occurring word is going to be the. Then you have these ellipses, like these three dots are known as ellipses in English. So this is also quite a lot. Then you have you, for, forwarded, all of these things, right? So this is what the frequency of our data set looks like. Okay. So now that we have done our EDA, let us do a train test split. Okay. Let us do a train test split. We're going to do the train test split to basically see can we correctly predict the next few words in our test data set, right? So we're going to take prompts from our test data set and we're going to see if our model is able to correctly predict it or not. Okay, so that is the idea behind this train test split. Now let us actually set up everything for next word prediction. Okay, let us set it up for next word prediction. The only thing I'm going to do here is I'm going to say train set.copy. So now I'm simply copying this train set into a new data frame so that it becomes easier to do. Okay. So Anil, remember I was saying that we have to evaluate our model. We have to evaluate our model. Remember that? So we basically discussed how to calculate perplexity and how to calculate cross entropy and things like that, right? The way we will evaluate our model is we will calculate the perplexity on the test set. So once we have gotten all our probabilities, we're going to use those probability values for the test set. We're going to evaluate the probability of each sentence in our test set, and the average of that is what we're going to return as the metric for judging whether our method works or not. Is that clear? So the test set's job is to tell us whether the perplexity is okay or not. So ideally, if I use a train set to learn my probabilities, to know if it is doing a good job, I have to go to the test set, calculate the perplexity there. If that is low, then it has done a good job. That's the basic idea. Okay. Now moving on, we now have a bigram model, right? Unigram model is going to be quite useless over here. It's going to just say every word it's going to keep predicting as forwarded, right? If you think about it, every word is just going to be predicted as forwarded. We're not even going to bother with unigram. We're going to go ahead and we're going to implement a bigram. Okay. Now to implement a bigram, we're going to make use of this function called bigrams from NLTK. So let me quickly show you where I have imported it. Okay. So the import is happening over here. Okay. So from NLTK I'm importing this bigrams, trigrams. These functions will automatically create bigrams and trigrams for us and store it in a set. Okay, that is why these two are used. So we're going to use these functions to basically create our dictionary. Right? We're going to use these two functions to create our dictionary. Let us quickly see how that's happening. So for W1, W2 in bigrams of sentence, right? For sentence in corpus. So I'm iterating through every sentence in my corpus. I'm basically saying for every word pair inside this, I'm saying bigram of model of W1, W2 plus equal to 1, right? So all I'm doing here is basically I'm incrementing the frequency of that. Okay, I'm incrementing the frequency of that. Now to calculate probabilities over here, all I have to do is I have to divide these frequencies by the total count, right? That's all I have to do. So this is how I'm going to do it. And this gives me my bigram model. Okay. So this build bigram model is going to create this frequency dictionary, which is going to hold these probabilities and it's going to return that to me. Okay. So we ran this function. It is giving none here because this is none here, right? So that is why you see that none over there. No big mystery there. Then we will use this get next word. This function is what will actually get the next prediction from this one, right? So let us see how this works. So if len of input string dot split is greater than 1, so the input string has to be greater than 1, right? For you to be able to calculate bigram probabilities, we say input string equal to input string dot split. Output is basically dict of model of tuple input string comma, right? And we're going to give the output of the maximum probability. So this sorted function is going to make sure that the maximum probability comes in the first position, because see, the reverse is true, right? And we're going to take the first word in that probability and we're going to simply return that. Okay. So that is what that is how we're doing. We're simply returning the word pair which had the maximum probability over there, right? That's all we're doing here. And if not, we're simply using the maximum this thing. So now here we're doing fallback. We're falling back to our unigram model and we're returning the word with the highest probability if the input string's length was less than 1, right? That is the case where your cursor is at the start of the sentence. Okay. So now let us see get next word bigram how. So the prediction that it's making is how to. Okay. The next word after they is they are. The next word after we is we have. The next word after what is what is. The next word after can is can be. Then you have I have a href, HTTP, www. This is kind of funny, right? The last three are kind of funny. Can anybody guess why we are getting this ahref? Why are we getting ahref? Anybody who knows HTML can answer this. How many people know anchor tag, right? This is HTML text. So in our body of our emails, right, it turns out that some people have put hyperlinks in the body and that is coming out as this. So that is why a cat, a dog is not happening. It is saying a href, which is kind of funny, right? So yeah, our bigram model isn't doing great right now. It's saying a href. After href, it is giving HTTP. After HTTP, I mean, HTTP is very predictable, right? If it is an href, I'll just explain this for those of you who don't know HTML, right? So guys, whenever you're writing a mail and you want to put a hyperlink, right? The HTML tag looks like this: a href equal to http :/ something, right? So this is a very commonly occurring thing in our email. Okay. Why is it not giving this equal to and this double quotes? Any idea why it's not giving these two? Because we removed it during our pre-processing, right? We removed these during our pre-processing. So what remains is a href HTTP. So this is the pattern that it has learned, okay? And this sort of tells us that pre-processing step should have included cleaning of URLs. So this is something that we learned post-hoc. So if we want to fix this problem with our model, we have to go back, we have to remove the hyperlinks that are present in our data, and we have to rerun this, okay? So I want you guys to probably try it, add that one pre-processing step there. You can use the code that we used in the first or second class to remove hyperlinks, okay? We had discussed one library which does that for you. So I want you to try this out if possible, okay? Moving on, let us now use the same logic to create a trigram, okay? Guys, the structure of the code remains the same. For W1, W2, W3 in trigrams, trigrams is a function which is from NLTK. It is simply updating the frequencies over here, and it's calculating the probabilities. Once we have built this trigram model, let us see what the predictions look like. Okay. So get next word for I may is I may be. Then we have can we get. Then we have I will be. Then you have will be a. Then we have be a good idea too. Right. So it looks like we have a pretty decent model which is predicting. Right. This seems pretty decent, because it's making meaningful sentences now. All these phrases that it's giving are not meaningless. So our model has to some extent learned how to capture 3 word level dependencies. Okay. So this is a good sign for us. Trigram seems to be working quite well. Now let us see if we can use these bigram and trigram models to get complete sentences. All I have to do is I have to keep adding a blank to the end of the previous prediction, and I have to keep getting the prediction, right? So all that this function is doing is it is keeping on going to add a blank at the end of the sentence, and it's going to ask the model to give you new words for that. Okay, so let's see how this works. So if I start with can we, let us see the sentence that we get using the trigram model. So can we get the best of luck in your group that we were, right? Do you guys see that this has stopped making sense? At which step did it stop making sense? Which step do you guys think it stopped making sense? Luck, right? Step 4. Yeah. So best of luck appears a lot, but then it ignores the long range dependency. It forgot that our first 4 words is can we get the, and then it just looked at this best of luck and it filled it there. So this is not very helpful. So okay. So we have noticed one problem in our trigram model. Let us see if the perplexity numbers corresponds to this. So this is an implementation of the perplexity formula that we had just discussed up. Okay, the perplexity of this works out to be this. So now for everything in my test set, I will have a trigram score and a bigram score. Okay, I can essentially look at these scores. The lower it is, the better it is, right? So it appears that my hold on, why is this happening? I would have expected this to be flipped. So let me just check if this has been implemented correctly. This is 1 upon 1, 0.001 times bigram, right? Okay, I guess. Oh no. It is doing the correct thing actually. So this is case when n-gram equal to 2. This is case when n-gram equal to 3. Need to figure out why this is happening. I would have expected this perplexity value to be lesser, but yeah. Anyway, let's sort of revisit this sometime next class. I'll sort of see if there's any mistake in this. If it turns out that it's correct, then I will inform you next class. But yeah, now let us talk about creating an n-gram model. Okay, you can create an n-gram model by simply using n-gram model. Okay, you can use this n-gram model from NLTK library to create an n-gram. Specifically, you can specify whatever size that you want, right? So over here now, we are going to use an n-gram model with n-grams equal to 4. So we're going to consider quadruplets over here. Once we train this model, let us see how the prediction works. How have you been able to get a copy of the letter agreement? So this is the sentence that it sort of predicts. Again, here it is able to do a slightly better job because it is looking at 3 previous words before it's giving you the next one, right? So this is how an n-gram would sort of predict. So according to you, like based on these examples, which one do you think predicts the best? Do you agree that the fourth one will probably predict the best? Do you guys agree that the 4-gram will predict the best? Because whatever sentence you get after 9 steps still seems to make kind of some sense. How have you been able to get a copy of the letter agreement? Like it's a proper sentence here, right? So 4-gram seems to give a pretty decent output, whereas my trigram gave me a very weird sentence. Can we get the best of luck in your group that were? It doesn't make sense there. But this has been able to give me a decent output. So this 4-gram has done a much better job, right? Okay, cool. So at the end of the day, the way to judge the best model is to actually compute the lowest perplexity score on the data. We have not written code to do this. Maybe we can talk about it a little later. Or what I could request you guys to do is maybe write a function here, like add a code block here. So let me just note this down. Homework, calculate perplexity scores for all the variants we have seen. Okay, the variants we have seen are bi, tri, and quad. Right? Okay. Yes, Anil. You will get these this notebook in today's notes. You will get this one only, so you can sort of do that. There are some other advanced techniques like LSTMs, transformers, etc., which we can use to enhance the accuracy of this prediction task, and we're going to study them as a part of this course, right? So I think 2 or 3 lectures from now, we're going to start talking about LSTMs, and towards the last couple of classes are going to be for transformers. We're going to specifically look at BERT. Okay, so BERT was actually the first model which was it BERT though? I don't remember the exact paper name, but transformer models were the first models where transfer learning worked for NLPs. Before that, we did not have anything like transfer learning for NLP. So until we come to this transformer models, we will not be able to apply transfer learning like techniques to do stuff. Okay, cool. So this concludes the content that is there for this lecture. Essentially, let us quickly talk about what all we saw today. We modeled the problem of helping people write emails faster as the next word prediction problem. Right? This was the problem business case that we tried to solve. We explored probabilistic language models. Okay, PLMs they're called. So we explored this. We auto-completed sentence by building bigram and trigram language models. We saw how to implement these concretely. We explored perplexity as a technique to ascertain the language model's understanding. I don't think we've done this. We've not really done this, so I'll probably not include this over here. We saw how smoothing and interpolation techniques can help overcome the disadvantages of out of vocabulary problem. Right? Let me just mention that out of vocabulary problem of vocabulary problem. And yeah, so this is all we saw. There are a couple of further readings. So there is one post-read which talks about the intuition and derivation of perplexity, right? So I briefly mentioned how to derive it when I was discussing perplexity. If you wanted to get the step-by-step derivation, you can sort of look at this. And we have this smoothing tutorial implementation over here from nlp.stanford.edu. Okay, so this kind of completes the content that I have today. I'm going to now start the doubt session. Whoever has doubts, please stay back. Those of you who don't have doubts can leave. Right? Happy weekend to you guys. I'll see you in next class where we will be looking at parts of speech tagging. Right? We're going to see how to tag parts of speech and stuff like that in next class. So let me take one question which is there in the questions tab. Anil has a question. Any strategy for revision of CV module? Anil, you can use the cheat sheet, right? Have the cheat sheets been rolled out? So let me just give you a quick demo of what the cheat sheet looks like. Have you guys received any cheat sheets in your dashboard? Guys? Have you seen something like a cheat sheet? Okay, no? Okay, one minute. I'll quickly show you what we have prepared. we have actually prepared a cheat sheet. Let me just quickly pull that off. That is, I feel, the best way to do this, right? Revise for this module. So we've spent some time and we've prepared this. Just give me 1 second. I had sent it to somebody. Huh. Just one moment, guys. I'll just get this from here. So, guys, we will be sharing this cheat sheet with you soon. Exactly how I think we'll be making it available through the Google Doc link. So, if you guys wish, I can pin the doc link over here, right? I can see if I can share this to anyone with the link, right? Yeah. So this is actually shared with anyone with the link right now. So let's do one thing. I'll paste this link over here today. You guys can take a look at this cheat sheet. Okay. According to me, this is the best way to revise computer vision. Every class that we have covered, the main concepts are sort of put here, right? So what is computer vision? Why use CNN over MLPs? What is CNNs? All this. So each concept that we have sort of studied is present in this cheat sheet. I request you guys to use this cheat sheet to revise concepts. So we have also done it lecture wise, right? So this is for lecture 4, this is for lecture 3. You don't have to go through the whole everything. You can just use this cheat sheet to revise. So please use the cheat sheet from this link to revise. Cool. So yeah, I hope that takes care of it, Anil. I'll mark this as answered, and yeah, I'll pause here for any further questions. You're welcome. If anyone has any further doubts, please let me know regarding today's lecture. Otherwise, we can end the class here. All right, guys, that's it from my side. Thank you so much for being an amazing audience. I will see you again on Monday. And yeah, happy weekend. See you guys. Good night.